Okay, welcome back, everybody. 1 minute, trying to let a couple more people in. Okay. Okay, well, welcome back. Couple of things. Well, actually, just one. Don't forget, exam number 2 due today at 10 p.m. Some of you already got it done. That's good. But again, just like the other, 75 minutes timed, approximately same number of questions, same type of questions. Most of them multiple choice and a few short answers. Any questions about that? Any questions about the chapters 4, 5, and 6? Yeah. If not, I will continue with chapter 7. This one takes a little bit longer time. There's a lot more stuff in chapter 7. All right, no questions? Well, yeah, so don't forget, give yourself plenty of time. Keep it simple. We're not trying to make it complicated. That is the exam, that is. Okay. So on my notes, we ended up on this chapter here, on this slide. But let me back it up for a little bit. We had just finished talking about covalent bonds. Now, as compared to ionic bonds, it's crucial that we're able to recognize what is what and how each one is made, because that's going to be used quite a bit down the road when we start talking about chemical structures and so forth, okay? And so when we talked about ionic bonds or compounds, CPD is short for compound. It is a combination of a metal and a non-metal. And it is a combination of the ions of the metal and the non-metal. And so we put them together with positive and negatives. They come together and they form an attraction action. It's not really a bond, but we call it a chemical bond. Because what we end up having, for example, we could have something like sodium with a plus charge, and we can have something like, I don't know, chloride with good old-fashioned table salt. And notice that here, it's just like two magnets coming together and attracting to each other. And we call that an electrostatic attraction. And that's the attraction between the positive and the negative coming together, okay? There's no sharing of electrons there. It's strictly an attraction between two ions, positive and negative ions. Now, one property about ionic bonds, ionic compounds, is that when we put them in water, to dissolve in water, they literally break up. So if I were to put sodium chloride in water and just dissolve it, I would break it up into their respective ions, okay? In fact, it would actually, if we had pure water and threw the ions in there, it would actually, that water will be conductive. It will conduct electricity because of the ions that we put in solution, okay? Totally break apart. Not all ionic compounds totally break apart 100%. Some may break apart maybe 5%. There's a degree of dissociation in ionic compounds, but nevertheless, all of them will break apart, okay? As compared to a covalent bond, okay, where we have a combination of a non-metal combined with another non-metal, okay? A good example would be carbon dioxide. Now, in this scenario, there is actual sharing of electrons between the two different atoms. And where we showed earlier with sodium chloride, what may be happening here, and I'm going to try to roughly demonstrate a bond, and we'll talk about this here in a second. that there is a sharing going on. Instead of these two coming together and just touching each other and attracting each other, there's actually an interaction between the two, and there's an overlap between the two species, depending on what they were, but both of them will be non-metal, okay? Now, the other aspect about these covalent compounds is, unlike the ionic compounds, when we place them into water, they do not dissociate. So if I take carbon dioxide and I just dissolve it in water, all I have is carbonated water. It's still carbon dioxide. It did not break apart, okay? Unlike sodium chloride. Now, there's only one exception where a covalent compound breaks apart, which we're going to talk about, and those are acids. But it's because the nature of the beast with respect to acids is that they break apart. But by and large, when they're not an acid, they're just covalent compounds, they do not break apart, they do not dissociate in water. And hence, if we were to check the conductivity, we will find that those covalent compounds would form are non-conductors, okay? They don't conduct electricity because there's no ions in solution, okay? And we have to be able to distinguish the difference between an ionic compound and a covalent compound, okay? And that's the main thing. Metal, non-metal combination, non-metal, non-metal combination for covalent. The other was for ionic. Okay, so when we talk about the types of bonds that are for covalent compounds, there's three types. There's a single bond, a double bond, and a triple bond, okay? And we would designate them by this line. So for a single bond, SB, we can do one or two ways. We can either use the electrons and draw two dots, okay? Or we can just simply draw a line, okay? Those, the same thing. You see us drawing lines to represent a single bond. For a double bond, notice a single bond has two electrons that are being shared between two nonmetals, okay? A double bond would have four electrons, and what we do is we draw two lines to represent a double bond. And then a triple bond would have a total of 6 electrons, denoted by the 6 dots, or we would draw 3 lines to designate a triple bond, with each line having 2 electrons, okay? Now, with respect to strength and energy, actually, the single bonds happen to be longer, meaning, if we were to look at a carbon-carbon bond compared to a carbon triple bonded, we will find that the triple bond will be shorter compared to the single bond, which would be a little bit longer, okay, with respect to the radius between the two atoms relative to each other. We also find that the single bonds are the weakest and have the less amount of energy, and triple bonds pack a lot of energy, quite a bit of energy. To give you an idea what type of energy here, a single bond could be represented by like butane. We're all familiar with butane, where you flick your lighter, you flick your bit. That's butane in that container, okay? Hot enough to light something up, but not hot enough to burn metal, like, for example, acetylene. Acetylene has a triple bond, carbon bond, triple bond, like that. That, in the presence of oxygen, burns very hot enough to cut metal. So acetylene torch is a hydrocarbon acetylene with oxygen, and it's hot enough to burn and cut metal. Okay. Now, with respect to bond length, when we get two atoms coming together, unlike the ionic bonds, where they just attract to each other, and the example I used previously was sodium and, let's say, chloride, okay? They're just attracted to each other because of the charge. So there's basically no interaction going on in there other than a kind of like a magnetic interaction between the plus and the negative, okay? There's an attraction. What was found is the following. For example, if we take a hydrogen atom, which has a known radius, calculated radius of 0.037 nm, which is nanometers, 10 to the negative 9 meters, very, very small. We're down in the atomic scale. You may have heard about nanobots. Okay, we're down to the atomic scale. We look at the hydrogen atom diameter, and if you, a radius, and if you look at the chlorine radius, which is 0.099 nanometers, we were anticipating that when they come together to make this compound here, HCl, which is the same compound that's roaming around in your stomach. In this case, it's called hydrogen chloride, but in solution, it's called hydrochloric acid. Okay. We were expecting that the total radius between the two was 0.136 nanometers. That is the sum of each individual radius, the hydrogen and the chloride. But it turns out that's not the case. It turns out that the bond length between the two nucleuses, the distance between the HCl nuclei and this, the chloride and the hydrogen is actually 0.127 nanometers, much less than the sum of the two. Well, that is expected because what we have is those electrons are being shared. Now, I can draw this with dots or lines. So if I go do this, I got two dots in the chloride, and then around the chloride, I will find, and we'll learn about this here down in a few more slides. We'll have more dots around the chloride because we're going to have about 8 electrons around the chloride, whereas hydrogen only has 2 around it, and those 2 are being shared by both the hydrogen and the chloride. So that distance here was expected to be 0.136, but it turns out it's much less. And that is the result of those 2 electrons in their overlap, okay? Where they thought they'd be, up against each other. That's not the case. There's overlap because there's a sharing of those 2 electrons between the hydrogen and the chloride. We're going to learn that there's going to be equal sharing and unequal sharing. In this example, there's unequal sharing. So those 2 electrons are being pulled more toward the chloride because of remember that property called electronegativity we talked about? Because the chloride is a lot more electronegative. It is pulling the electron density toward itself much more than the hydrogen is pulling it toward it. Okay. All right. So the sum for the bond length between 2 nonmetals turns out to be less than the sum of the individual radius of each atom because of that overlap that's occurring between electrons in that bond. All right, so let's talk briefly about bond energy. Energy is required when we need to break or form a bond. There's energy involved here. Okay, it's not a spontaneous thing. So the energy has to come from something. So, for example, if we need to break a chemical bond, we got to put energy into the system to break that bond. Okay, and so energy is treated as a reactant. And that being the case, what is happening is it is taking energies is being absorbed. So we call that was an endothermic process. Endothermic, endo meaning energy is going into the system. And in fact, when you do a reaction that's an endothermic process, the actual container will get cold because it's taking energy away from the system and putting it into the reactants. Classic example of this would be a cold pack that you can buy at, say, the pharmacy. You take the cold pack, smack it, the chemicals in there dissolve and they interact, and the pack gets cold. Now you can use that cold pack on your muscles and so forth, okay? So we call that an endothermic process, and heat is a reactant. Remember, to the left of the arrow, this represents a process, either a physical process or a chemical process. To the left of the arrow are the reactants, to the right of the arrow are the products. So in this case, heat/energy is a reactant, okay? And this example here, HCl is being broken up, okay? It's being broken up to generate the hydrogen atom and the chloride atom. And when we break that up, you end up with a hydrogen with its electron. And guess what? The chloride, if you recall the picture I draw earlier, the chloride is in group 7 valence electrons around it, right? So there, the 7 dots around the chloride. Hydrogen has 1 electron, okay? Notice here, when it comes and it interacts, you form a bond here. Form 2 electrons are going because there's an orbit on the hydrogen, there's an orbit on the chloride that is empty, the p orbit. So that electron can actually fit right into the p orbit very readily to form a bond. Okay, you form HCl. So anyway, this is an example of endothermic where we are breaking that bond. Okay. Now, when bonds, when bonds are formed, energy is always released. And with energy being released, we call that an exothermic. EXO is energy is exiting the system, and therefore it actually gets warm. Again, another example would be a hot pack, chemical hot pack that you can go to the pharmacy again, get that hot pack, get it, smack it, chemicals are released, and this time that pack, because of the chemicals in there, gets warm because its bonds are being forming to generate a compound, and it's giving off energy, and it's hot. Now you can put that on your body to do whatever as far as your muscles or strained muscles are concerned. Ice pack, cold pack, ice pack, cold pack. All right, so here, energy is treated as a product. So in this time when we write the process, and that's the opposite of what we did up on top here, where we got the hydrogen atom combining with the chloride. So here we go again. We've got a hydrogen with a 1 dot and the chloride with 7 around it, okay? Or you can form a process here. So it eventually goes on to form a bond. And I'm putting dots in here to kind of demonstrate what's going on here with the electrons. And notice something interesting. Around the chloride, there are a total of 8 electrons. Of those 8, 2 of them are being shared with the hydrogen. So the octet has been fulfilled for the chloride. The hydrogen has 2 of them that are shared with the chloride. And for hydrogen, its rule is a duet. Okay, so you would never find hydrogen with more than 1 bond. So put that in long-term memory. Hydrogen will always only have 1 bond, 1 pair of electrons bonded to it. Okay. Exothermic. So regarding these type of questions, here you have a compound which is H2S. What it is not important. Okay, we don't need to know what it is at this time. What we do need to know is recognize what type of compound we're looking at. We're looking at hydrogen and sulfur. So with that information, can you tell me if it's an ionic compound or a covalent compound? What do you guys think? It's HCl, H2S, an ionic compound or a covalent compound. And it's this one right here. What do you guys think? Think about the criteria for being ionic. Think about the criteria for being covalent. And that is correct, Thomas. It is covalent. So H2 is covalent. And so these bonds, these electrons are being shared, okay? That's the deal. If it was ionic, there's no sharing going on there. We got separate charges and they're just being attracted to each other. So in this scenario, being covalent would answer the first question, and that would be a true statement. Yes, electrons are shared in this compound, H2S. Okay. The next one, the bond between H and S, is it ionic? Well, we answered it that it's covalent, so that should just tell you that that's a false statement, okay? Because it's covalent, which is a combination of 2 non-metals, hydrogen and sulfur. And then the HS bond length is less than the sum of the 2 atomic radii. The fact that it's covalent, this will be a true statement. okay? Because there's that overlap, that sharing of electrons between the hydrogen and the sulfur. And then breaking the HS bond releases energy, okay? Now, what do you guys think? Break the bond, remember, it requires energy, so that would be a false statement, okay? It wouldn't release energy, it requires energy. Okay. Well, those are the type of questions you might be asked concerning energy and bond lengths and so forth. Which brings us to what I kind of just introduced to you when I was showing you the chloride with the dots, the electrons around it. That represents a certain type of structure, okay? We call that a Lewis dot structure. And what that does, it identifies the number of valence electrons in the outermost shell. Now, for only the A elements, okay, only the A elements, this is true. We know by the group number how many valence electrons they have. We don't know that for the B's, okay? Only for the A's, which are those. We can't predict for the D block or the F block because it varies. It basically varies. Okay, so we're going to learn how to draw Lewis dot structures for the atoms, and then we're going to take that and learn to draw structures for compounds. Okay, well, the first step first. Okay, group number gives us the number of valence electrons. Okay, and the way we do this is we simply take the atom and think of the atom as a square box, a box. Okay. And so let's say I'm going to just use the symbol S for SY for the symbol. Imaginary square box around it. Okay. And we simply just put the dots around. So we put one dot on each side until we go around the horn, and then we double up on the dot. Now, if you go clockwise, counterclockwise, makes no difference. You start on top, you start on the bottom, left or right, makes no difference. Just start someplace. Okay. And so let's say I got a hydrogen. Hydrogen has one valence electron. So we put a dot. Okay, that will be hydrogen's Lewis dot structure as that. Now, let's say we go to the next one, which is helium. We go around the horn, we go to the next side. So that would be helium with two dots. That's the Lewis dot structure. We keep going around the horn. We got 3 valence electrons there, 4 valence electrons there. That would be a good example for carbon, where you put the symbol carbon and 4 dots around it. Now, once we pass carbon, we have nitrogen, which has 5. Now we can double up. Which one you want to double up on? No difference. Just double up on one of them. And there's nitrogen. Okay. And we keep going around the horn. So we got 7. 1, 2, 3, 4, 5. Then we got 6 valence electrons, 7 valence electrons, and finally we end up with the one with 8 valence electrons. So all the noble gases would have the Lewis dot structure with 8 dots around. Okay. And we just go around the horn like I stated. Where you start on that makes no difference. And you don't have to put a dotted line. That's just to demonstrate that you put 2 dots. So basically, if you ended up with, 2 valence electrons, that wouldn't be the correct format. With 2 dots side by side, the correct format would be a dot there and then a dot next to the side. Okay. And that just follows the principle of filling up the electron shells, starting with lowest energy and moving up to higher energy. Okay, so in this example, they want to determine the Lewis dot structure for the following: for potassium, oxygen, silicon, magnesium, iodine. So we write down the symbol, which is K. We know that potassium is in group of 1A. So 1 dot. Okay, which side you put it on makes no difference as long as you got one dot somewhere. Oxygen is in group, 6. So we go 1, 2, 3, 4, 5, and 6. Okay. Oh, should be a little bit. Let me read all that a little bit better. 1, 2, 3, 4, 5, and 6. All right. And then we have silicon, group 4. We got 1, 2, 3, and 4. Magnesium's in group 2, so we got 1 and 2. And then we got iodine in group 7. We got 1, 2, 3, 4, 5, 6, and 7. Okay. Which would be the same Lewis dot structure for chlorine. Okay. Same thing because everybody in that group shares the same number of valence electrons. Sodium will be same thing as potassium, etc. Okay. So nothing complicated, it's just straightforward. Find out what group number it's in, put in the dots, and you should end up with something like that. For the Lewis dot structure. Now, knowing how many valence electrons is important because we're going to take that information. Okay, we're going to start building. We're going to be given a formula, and from that formula, we're going to be able to determine the structure. Okay, the structure, which brings us to the Lewis dot structures. Now, it's important here that if you haven't done so yet, to make sure you print out the shapes table. Okay, because that's where we're going to use this extensively. In the shapes table, from the Lewis dot structures and the valence electrons, we're going to put together a tentative structure. Okay. From that structure, we're going to generate a generic formula, which has the letters A, B, subscript X, and E, subscript Y. Okay. A is constant. That's the central atom. You're going to be told who the central atom is. Either it's going to be underscored or be in bold. Okay. So that is a central atom. Then whatever follows after the central atom is bonded to the central atom. And that is represented by the letter B. In the subscript X, it could be 1 element or 4 elements. It depends on the compound, anywhere in between. Okay. And then E represents what is called the lone pair of electrons on the central atom, which in this case is A. Okay. So you can see this drawing right here, where you have a lone pair on the central atom. These are electrons that are not bonded to anything. They're just sitting on the central atom. And you can have a maximum of 2 pairs. That is an example of 1 pair. But you can have an example where you got 2 pairs in the central atom. And that is given by the letter E, where Y can be 1 or 2. Now, B, they don't have to be, whatever is bonded to the central atom can be the same element or a mixture of elements, okay? B is just a generic letter to designate how many atoms are bonded to the central atom. So once we know the general formula which we obtain from the Lewis dot structure, then we know the generic formula. We come to the table, which now gives us the geometry. For example, we end up with AB4. Here's the geometry where we got A sitting in the middle, and then B is bonded, okay, to the central atom. That line represents a bond between the A and B. And remember that bond has 2 electrons. And if, for example, these Bs were all 4, let's say, magnets of opposite sign, they're going to want to repel each other. So what happens is they repel each other. Those electrons repel each other until they get at the furthest away position that they can, because they're repelling. And when that happens, when there's 4 moieties bonded in the central atom, you end up with that particular shape, which is the most common shape there is with respect to molecular structures out here. And then a bond between the B's, a very specific bond of 109.5. Now, when we get into lone pairs, well, lone pairs are not bonded to anything. They tend to want to take more space because you got 2 electrons in there and that orbital sticking out there that repel each other, okay? And the result is that because of that, that bond angle can get much less than 109. So here we had earlier the example of a tetrahedral. That's the name of that particular structure, geometry, and that's the bond angle. But if we take out one of these B's and replace it with a lone pair like we do down here, we have this structure, AB3E. Well, those lone pairs take up a lot of space, okay? And they cause the other bonds to be pushed down, resulting in that bond angle to be much less than 109. So lone pairs have quite an effect on the properties of the molecule, okay? Lone pairs play a very crucial role on specific properties and why compounds have certain properties. All right. So what we do to figure out the structure is, one, we tally up all of the valence electrons that are brought in to the table, so to speak, from all of the atoms in that count, okay? Once we know that, we take the central atom, which has been designated, and then we attach all the other atoms to the central atom and draw a single line between them, okay? Now, the important part about the total number of valence electrons, if, for example, you end up with 10 valence electrons, then that is a number etched in stone. That is what you got to work with. You cannot magically just take out 2 or add 2 as needed, okay? Because that number came from the atoms that are involved in the structure. And you start off with 10. When you're done, you should end up with 10. And as we're always doing an inventory and keeping track of our electrons that we're building the structure, because it's easy to lose a pair or add a pair and then really mess up our structure completely, okay? So once we put the central atom and then bonded everybody to that, then we count the valence electrons, and then we follow and see if everybody's happy with respect to the octet, to make sure that all the atoms involved have 8 electrons around. Those 8 electrons can be non-bonding pair or could be a bonding pair. For example, the one we just did was the hydrogen, 2 electrons, and then the chloride. And there was 6 electrons around it that were not bonded. These are the lone pair. You got 3 lone pair LP, okay? And these are the bonded pair. Okay, now around the chloride, there are 8 electrons. There's 8 electrons. Of those 8, 6 of them are the lone pair. And the other 2 are the bonded pair. Okay, so it's a total of 8. So the octet has been fulfilled for the chloride. With respect to hydrogen, there are 2 electrons that are being shared with the chloride. So those 2 count toward both the chloride and the hydrogen. And so hydrogen now, its rule is a duet. So hydrogen is fulfilled. The big takeaway here is this: hydrogen will only have one line to it at all times. You won't ever see hydrogen with more than one line, okay? Because there's the duet for hydrogen. It's not an octet. All right, so then after we got it all put together, we check to make sure we still have the same number of valence electrons we started off with. And then looking at the central atom, we then identify any bonding electrons and lone pairs, because from that information, we're going to create the general A, B, X, E, Y formula. And that takes us to the table to figure out the geometry, okay? Now, if we're done and we've put all the lines that we can and we check the octet and we don't have enough, somebody's missing electrons, well, we don't magically just pull one out of there and stick it in there. No, what we do is we take from the neighbor who may have extra, necessarily extra, may have some non-bonding electrons and create a double bond and have those electrons on one atom shared to share it with the atom, the central atom, back and forth, okay? If the double bond doesn't work, then we look again for another set. We may even have to make a triple bond. So that by sharing, then everybody has the octet fulfilled. And we're going to do an example of that to demonstrate that, okay? All right. It's probably easier just to do an example. All right, so here we have H2O, water, okay? And so oxygen is our central atom. So the first thing we do is we tally up all the atoms. And remember, we did an exercise way back when where we said, okay, we have this particular formula here, and we're not concerned about what it is and so forth. We just want you to identify how many of each atoms we have. So in this case, remember, we had 3 hydrogens, we have 1 phosphorus, and we had 4 oxygens, right? Remember that exercise? Well, this is why we did that, because we need you to identify how many atoms are in that compound. So we got oxygen, we got 2 hydrogens, okay? Now, the total number of valence electrons, TVE, total number of TMVE, maybe total valence electrons for every atom that makes up the structure. We have 2 hydrogens, each one brings in 1, okay? So we have total of 2, okay? We have 1 oxygen. 1 oxygen is in group 6, okay? So it brings in 6 valence electrons. So we have a grand total of 8 valence electrons to work with. Now, that number that you get should be divisible by 2. And when you divide that number, you should get a nice even number. In this case, 4 PR, meaning pair. I choose to work with pair because I can draw a line that represents a pair rather than having to sit there and put all these dots, okay? You can lose those dots easily. So I got 4 pairs to work. Now, oxygen is the central atom. So once you identify the central atom, you can draw that, okay? And then the 2 hydrogens are bonded to the central atom. So I just go make a line on one side, make a line on the other side, and attach the 2 hydrogens, okay? So that takes care of 2 pair. So I got 2 pair to work with. That's what's left over. 2 of them, 2 pair were taken care of when I added the hydrogen. So I got to put 2 pairs someplace, okay? Now, I can't put them on the hydrogen. Why? Because the hydrogen's duet has been fulfilled. So the only logical place to put those 2 pairs have to be on the oxygen itself. And I can very quickly just draw 2 lines there, and I have my 4 pair. Now you can draw the 2 lines if you like, or I can draw the 2 dots for that. Either way, it's the same thing. I prefer the lines, but whatever you're comfortable. Now go back and check to make sure you still have 4 pair. So I got 1, 2, 3, and 4. That's what I started off with. That's what I ended up with. I don't have to go any further. I'm good. Okay. If you do an inventory, you end up with 3 pair and you've got 4, then something went amok. Go back and check your numbers, okay, or vice versa. Maybe you added too many valence electrons. You end up with extra pair. Instead of 4 pair, let's say you got 5 pair. Well, think about it. Okay. Let me draw it here. Let's say you did the math and you added up and you took care of 4 pair and you calculated 5 pair for whatever reason. you're like, okay, I got one pair to, where did I put that? Well, think about it. Is it logical to put it any place? And the answer is no. Why? Because the hydrogen is happy now. It's got 2. The oxygen now has 8 around it. I cannot put 10 around it. That violates the octet rule. So that means that this number is incorrect. So you got to go back and check your math to make sure, here's small numbers, but you can get higher numbers down the road, and you really got to keep track of your inventory. On the same token, what if I ended up with 3 pair? Okay. What if you ended up with 3 pair and all you can do is the following like this, because you ended up with, in your account, you had 3 pair. Well, that, and you, like I said, you can't add any more. So you come to this formula and you're like, okay, I got 3 pair here, but I don't have enough electrons to fulfill the oxygen, because now I only got 6 around oxygen. Okay, and I cannot magically just throw in 2 if I'm coming up with 3. So that should flag you to say, maybe I did my math wrong. Okay, so those are little flags. Either you add too many electrons, okay, and you end up with extra and there's no place to put them. So that's an indication that maybe you counted wrong with valence electrons, or instead of, you selected the wrong number from the group it's in. And then the other direction is you got too many and you can't put them any place, okay? Because you should never, ever have 10 electrons, anything less or more than 8 around an atom, and nothing less or more than 2 around hydrogen, okay? So you won't see 10 electrons around a central atom. And if you put 10 electrons around it, it gets marked wrong, it's incorrect. All right, so this is a rehash of what I just talked about, okay? So what this does is this, let me take one more step. So I ended up with this structure right here, okay? So now, once you got this structure, you go to the general structure. Okay, we got A, which is always there, and then we got B subscript 2, because there are 2 atoms bonded to the central atom. Then in this case, we got E's, because those are lone pairs on the central atom, which is oxygen. So we got E2. So that, ladies and gentlemen, is our general formula that we determined from the formula we came up with the valence electrons, okay? Now, what do we do with that bit of information? We take the AB2E2 and we go to the shapes table. And we look for the AB2E2. And there it is. AB2E2. Here is oxygen, and here are the 2 hydrogens, okay? And here are the 2 lone pairs on the central atom. That particular structure is called band, and that bond angle between the hydrogens is much less than 109.5, okay? And that is because those lone pairs take up a lot of space. This is our kind of our default structure. Majority of our compounds have this tetrahedral shape. And the moment I remove one of these species, whatever is bonded to it, and leave a lone pair, what that does is causes that bond angle to get small. Okay, because those lone pair take up a lot of space. They take up more space, so it shrinks the bond angle down the road here. And if I got 2 lone pairs, that bond angle gets shrunk even more. So this is like more of a double less, much less than 109, because of those lone pairs, which play a big role in the properties of the compounds. Affects their all kinds of properties that come into play, okay? Which we're gonna definitely learn about. Okay. So that is our formula. Our general formula was AB2E2. And we learned, oh, did I say that I got ahead of myself? Sorry about that. And so that is the general formula. There is a structure. Its name was bent. Yeah, I guess I did that. And the angle is less than 109.4. Okay. All right. So what we have here are, for example, 4 compounds. They're all covalent compounds. Okay. And what we're going to do here is we're going to try to figure out a structure for them. All right. So step number 1, we got the first one, HCN, which is poisonous gas, by the way. Okay, first things first. We tally up the valence electrons. So working on this, we got hydrogen, 1 hydrogen, which brings in 1 valence electron, 1 carbon, and yes, it's redundant here that I'm writing this out long ways. Again, my approach has always been a systematic approach. And then as you become more comfortable, you can make your own shortcuts. So carbon is in group 4. So it brings in 4 valence electrons. And then we have 1 nitrogen, which is in groups 5. Okay. So we have a total of 10 valence electrons divisible by 2. We have 5 pair of electrons to work. Okay. 5 pair. Or a total of 10 individual electrons. That is the number we got. We cannot add to it. We cannot subtract to it. Okay, that's what we got to work. Okay, we're told here that carbon is underscored. So that means that carbon is a central atom. So we can draw carbon. And then on each side, we have a nitrogen and a hydrogen. So we can draw a line and hook and put nitrogen, draw another line, represents that bond with hydrogen. Okay, so that took care of 3 pair. Excuse me, 2 pair. I meant to say leaving 3 pair to work with. Okay, see how I'm keeping track of my inventory there. I start off with 5. I use 2. I got 3 to go. Now, where to put the 3? At this point, you know you can't. As I stated, you can't add any more to hydrogen. Hydrogen now is happy. Okay. So where you put them on the other atoms is any place, your choice. I prefer to put them on the outside atoms and then work my way in. So with that being said, I go 1, 2, and 3. That takes care of the last pair. So now I got 0 pair. Now I go back and check. Always keep track to make sure you still maintain the 5. I got 1, 2, 3, 4, 5. I still got 5 pair. Okay. All right. So with that, now go check the octet. Well, we know hydrogen's good to go. Okay. Nitrogen's happy too, right? Because it's got 2, 4, 6, 8 electrons around it. The way it is, 2 of them are being shared with carbon and the other 6 are not being shared. We look at carbon, well, carbon only has 4 electrons that are being shared, 2 with hydrogen and 2 with nitrogen. So there's a disparity here, right? So this is where we start creating double bonds. So we take from Peter to share with Paul, so to speak. So nitrogen, we can take one of those, and let's just, for argument's sake, just take this one and move it here and create a double bond, okay? And so now what we have is carbon, double bonded nitrogen, and then we have the 2 lone pair, and then the hydrogen. So do we still have 5? 1, 2, 3, 4, 5. Yes, we do. We're still good. Okay, go check your octet. Nitrogen still maintains 8. So we're good with nitrogen. Okay, 2 of them, 4 of them are being shared with carbon as a double bond. And 2 of them, 4 of them are being on nitrogen. Okay. Hydrogen's still good to go. Now we look at carbon. Carbon now has 6 around. Okay. Still has not maintained the octet. So what we do, we repeat the process. Okay, and this time we're going to take this lone pair and create a triple bond. So now we got carbon, 1, 2, and 3 nitrogen, a single pair, and then back. Okay, go back and verify your starting number of valence electrons. 1, 2, 3, 4, 5. We're still good to 5 pair. Still good. And this is why you check at every step to make sure you didn't lose anywhere pair or by mistakenly add another line. Okay. So we got 5 pair. We're good to go. Now check the octet. Okay, we're still good with nitrogen. Nitrogen has 8 around it. 6 of them are being shared with carbon, and 1 of them is on the nitrogen side. Okay, carbon again now is happy. So okay, because 2 of them are being shared with hydrogen, and the other 6 are shared with the nitrogen, and then we can see the hydrogen is happy. So that is the formula that we come up with of hydrogen HCN. H, single bonded carbon, triple bonded nitrogen, and I just go ahead and put 2 dots there, okay? Now, with that, we now create the general formula, which is straightforward here. It's A, always A, and B2, okay? There are no lone pairs on the central atom of carbon. There's a lone pair of nitrogen, but nitrogen is not the central atom, so we don't care about that. Only on the central atom, which is carbon. And so the general formula for this species is AB2. With that information, we go to the shapes table and we search for AB2, and there it is right here, AB2. It has, its name is linear, and that bond angle is 180 degrees. So here's carbon right there, here's nitrogen right there, and there's hydrogen right there. Bond angle 180 degrees. The geometry is called linear. Okay. All right. And that is the formula. All right, now I'm going to do one a little more meat to it, so to speak. All right, let me change the color here. Go back to yellow. We have, this is a hydrocarbon. It's what's called a fluorinated hydrocarbon because there's fluorine attached to it. And so what we have is 1 carbon, which brings in 4 valence electrons, right? It's in group 4. All right, again, we have hydrogen, 1 hydrogen, which brings in 1 valence electron. And now we have 4, oh, excuse me, I've got 4 in the head, 3 fluorides, okay? Each fluoride is in group 7, okay? So 3 times 7 is 21, right? Tally this up, 4, 5, 6. 26 electrons, valence electrons to work with. Divide that by 2, we have 13 pair is what we're going to work with. 13 pair. The central atom is carbon, so we can put carbon. And then we have the hydrogen and 3 fluorides quickly attached to it, okay? So we can quickly go draw 4 lines and put the fluorides there and the hydrogens. So that takes care of 4 bonds. Okay. Let's stop for a quick second. I get to get something real quick. Okay, I'm back. Sorry about that. Anyway, so as I was saying now, we've taken care of 4 of those pair, which leaves me 9 pair to work with, okay, of the 13. So now those 9 pair, think about where you're going to put them, okay? Obviously, we can't put them on the hydrogen. Remember, hydrogen only has 1 bond, always will have 1 bond. Take a look at the carbon around it. Carbon already has 8 electrons around it. There's 4 single bonds. It's a total of 8. So carbon is happy. So the only place it can go has to be on the fluoride. Okay. And so I'm gonna make them a little bit different color so we can distinguish the pair. And so I'm just going to start on the outside and just add 9. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9, 10, 11, 12, 13. 13 pairs what we started off with, 13 pairs what we got. Okay. So that works fine. We've taken care of. I cannot add more or subtract anything less than 13 because that is the number we come up with based on the number of valence electrons that all of the atoms brought in through the structure. Okay. So that is what we got. 13 pair. Now let's figure out the general formula. We have A, which is the central atom, and then we have B, which would be a 4, B4, AB4. Does make a difference that we have a hydrogen and a fluoride, okay? B is whatever's bonded to the central atom, be it whatever atom, and there's four elements bonded to the central atom. So we have the general formula of AB4. With that information, we go to the shapes table and look for AB4. And there it is right here, AB4. It is tetrahedral. The bond angle is 109.5. Here's carbon. That could be hydrogen, and then the other fluorides around it, okay? And tetrahedral. All right, so that is the formula. Now, here's an interesting one. Good old-fashioned carbon dioxide, okay, CO2. So we have 1 carbon and 2 oxygen. So again, carbon brings in 4, and oxygen is in group 6. So that brings in 12, right? 12 valence electrons. So we have 16 valence electrons divided by 2 gives us 8 pair to work with. 8 pair to work with. Okay. Carbon's the central atom. So I can very quickly put carbon down. Then I got 2 oxygens bonded to them. So I can just go on each side and put 2 oxygens. So that takes care of 2 pairs. So I got 4 pairs to work with. Okay. Okay. So now the question is, excuse me, I can't even say that. Somebody didn't catch my math here. 8 minus 2 is 6 pair. 6 pair left. Okay, to see if you're not careful, you can easily make a mistake with your valence electrons. But at the end, it'll show up. You hopefully pick it up. So I got 6 electrons, pairs to work with. So what I do, like I mentioned, whatever I get, I fill in the electrons on the outside elements bonded to the central atom. So I go 1, 2, 3, 4, 5, and 6. Okay. And I double check to make sure I got 8. I still got 8, so I'm good to go. Okay. Now I check my valence, what do you call it? My valence electrons, right? Now, if I look at the oxygen on the left, there are 8. Okay, octet's full. Look at the oxygen on the right, I got 8. Okay. I look at the carbon, I only got 4 around carbon, okay, which are shared with the oxygen. So what I got to do, I need 4 more. And guess what I do? Just like we did for the first one, we share. Rob, we share from Peter, give to Rob, whichever you want to look at it. So we're gonna take 1 pair because we need 8. I'm gonna make it so I just take 1 pair from each oxygen. I'm gonna take 1 pair and make a double bond here. I'm gonna take 1 pair and make a double bond here. Okay. And when I do that, let me make some room here. When I do that, I end up with a carbon, double bonded oxygen. And then I have my 2 electrons. And now let's double check. Do I still have 8 pair? 1, 2, 3, 4, 5, 6, 7, 8. Still good to go on the 8 pair. Okay. Check my octet, oxygen. I got 8 around oxygen. I got 2 of them, 4 of them that are shared with the carbon as a double bond, and 4 of them that are a lone pair, not bonded. And the same is true with the other oxygen. 4 of them are bonded to the carbon and 4 of them are not. And then the carbon itself also has 8. 4 bonded and shared with the oxygen on the right, and 4 are paired with the oxygen on the left. So that is our formula, our structure. Our general formula would be simply AB2. There's no lone pair on the central atom, so it's AB2. Okay, and so then that sends us to the shapes table and looking for AB2. Okay, which is right here. And so that's carbon and there's oxygen. Okay, that bond angle is 180 degrees. It's called linear. Okay. Now, the structure plays a very important factor on the properties, because we would anticipate CO2, that's the formula for carbon dioxide. We would anticipate, due to the dipole moment, I don't want to jump on that. I'll wait for that. But the point is this: without knowing this information, we would assign this with some totally different properties, okay, that carbon dioxide would have. But because of the structure and its geometry, it has certain properties that would not be expected. And the only way we can determine that is to actually find this geometry. Okay. So, all right. So let's do this last one. We'll call it a day here. Get back up, make some room. So we got the last one is ammonia. Okay. NH3, nitrogen, 1 nitrogen, and 3 hydrogens. Valence electrons, again, nitrogen brings in 5, and there's 3 for the hydrogen. So we have a total of 8 divisible by 2. We got 4 pair to work with. Okay. Nitrogen is the central atom. Okay. And so then there's 3 hydrogens bonded to it. So we can quickly add 3 hydrogens with a line, and that takes care of 3 pairs. So we got 1 pair to work with. Now, the only place to put that pair definitely has to be right on the central atom. Okay. Central atom, there's no place. We can't add it to the hydrogen. That would violate its duet rule. So the only place is nitrogen. Now we check the octet duet. Hydrogens are all good. And the nitrogen has 8 electrons around it. 3 of them are bonded and 1 is a lone pair. So the general formula would be A, B, 3, because there's 3 things bonded, 3 atoms bonded to nitrogen. And then this time we have an E, because that is the lone pair on the central atom. So that is our general formula. And then we take it to the shapes table, look for AB3E. And there it is. AB3E. Here we got nitrogen in the middle, and then the hydrogens around it. Okay. And that has a specific name called trigonopyramid. And that bond angle is much less than 109.5. Again, because of the lone pair. They're taking space and causing that bond angle with the other species to shrink. Okay. That being the case, the fact that you ended up with a lone pair on the central atom really gives a certain character to the overall property of that molecule, which we're going to learn about. Anytime you do a Lewis dot structure and you end up with a lone pair on there, there are certain properties you can say automatically, this is it. Okay. All right. Well, the next one deals with there's what I just did for HCN. Okay, I went through it, added up all the valence electrons, so forth. We ended up with 5 pair, and it created the 2 bonds for hydrogen and nitrogen. Okay, check the octet. Then we made triple and double bonds as needed, and that was it. Okay, I think I'm going to stop it here because the next step is to make Lewis dot structures of the polyatomic ions. And you might say, what are polyatomic ions? Well, I direct you in preparation to the periodic table on the left side where you see most common polyatomic ions. You may want to be familiar with those. We're using those quite a bit. Okay, I did kind of briefly mention those and stating that those are units. Those are units that we use individually. Each have, that's a unit. We don't take them apart. If we need more than one of those units, we put a parentheses around the whole thing and we put a subscript if we need more than one. Okay. So be familiar with those, because what we're going to do is we're going to learn how to do the Lewis dot structures for these polyatomic ions. And it's the same step, except the one difference is we're going to add we're going to add a value. We're going to add to the number of electrons or subtract depending on the charge that they have. Notice these ions are either negative or positive charge. Okay. All right. So let me stop it here. Any questions?